Hello, my name is Madeline Lucey. I'm a graduate student at UT Austin, primarily working with Keith Hawkins. And today I'm going to tell you about my work on the chemodynamics of Milky Way bulge stars. I've primarily focused on metal poor stars, and that work has been published as the Combe survey. But today I'll also talk about my more recent work, which does look at the dynamics of all bulge stars. And this work has been in collaboration with a lot of people that you can see listed here, and also many others. And so big thanks to all of them. So one of the main reasons I'm really excited about the inner galaxy is because there are predictions from simulations that the oldest stars in our galaxy are primarily going to be in the center of the galaxy. And so here, these three lines in each plot correspond to three different simulations from the fire simulations, Milky Way-like simulations, so they're the latte suite. And in the top plot, what you're going to see is the number of stars as a function of distance from the galactic center that formed before a Z of 5. And so you can see we have the peak in the center of the galaxy. So you're going to find most of the stars in our galaxy that form before Z of 5 are going to be towards the center. And then this bottom plot, what we actually look at is the fraction of stars at that radius that formed before Z of 5. And so that's why people have historically gone to the halo to look for the oldest stars, is because the fraction is higher in the halo because there's just so many stars in the center of the galaxy, even ones that weren't born before Z of 5. And so it kind of, you can't really, the fraction is much lower in the center of the galaxy. And then on the right plot, the key point here is then if we can make a metallicity selection, so we're only counting stars in the galaxy that have metallicities less than -2. And then if we look at the fraction of that, so the fraction of stars that have metallicity of that are less than -2 that form before Z of 5, then we see that the center of the galaxy is actually where the higher fraction is. And so that means essentially, if we can select metal poor stars, we have a better chance of finding old ones if we go to the center of the galaxy rather than the halo. So what we need to do is we have this huge haystack of metal-rich stars in the center of the galaxy, and we need to look for our proverbial needle, which is going to be our metal poor stars. And so they're going to be this tiny fraction of all the metal-rich stars in the inner galaxy. But luckily, we have a magnet, which is this metallicity sensitive sky mapper photometry, which we can use to grab those metal poor stars and now get to be able to study them. And now that we are able to target these metal poor stars, we want to use them to study their chemodynamics to figure out the origins of those stars. And really what we want to make sure is, or study about them, is whether they belong to a classical bulge component. It's still not known whether the Milky Way has a classical bulge component or if it's just a boxy peanut bulge. And so in this case, the boxy peanut bulge is a result of just secular disk evolution, whereas the classical bulge would be more of a signature of hierarchical growth. Or there's also the possibility of these metal poor bulge stars are simply just the inner halo. So just halo stars that spend most of their lifetimes very far from the galactic center, but are currently just passing through the center of the galaxy on their orbits. In addition to the kind of structural possible origins, there's also theories that the metal poor bulge stars are made up of completely dissipated globular clusters, so ancient globular clusters that have been disintegrated. Also possible of disintegrated accreted systems that were created very early on. There's been recent papers claiming discoveries of accreted systems in the inner galaxy. And then there's also the possibility that we do find some nucleosynthetic yields of the first stars in these stars. And so we'll figure out if they're really second generation stars. And there's also theories that maybe even a real population 3 actual first star could be in the center of the galaxy if it still does exist today. Right, so what we know already from the line of sight velocities of the metal-rich bulge stars, this is from the Argos survey, so this is Argos data printed here. And then we know the line of sight velocities actually reveal that most of the mass in the inner galaxy is part of the boxy peanut bulge. So we see signatures of rotation in those, and we also see the boxy peanut bulge signature of a peaked dispersion, velocity dispersion at the galactic center. And so we know most of the mass in the inner galaxy is in the boxy peanut bulge. But there's been studies showing that maybe the metal poor stars may actually be part of a classical bulge component, because we see this much higher velocity dispersion amongst these stars, which is kind of consistent with a compound bulge signature, indicating that there's an overlapping classical bulge component. However, as this paper points out, it's also possible you could just add a 5% halo component in here, and so that would also create that signature of a higher velocity dispersion. So we kind of have this degeneracy here where do the metal poor stars have a higher velocity dispersion because there's a classical bulge component here, or is it just those halo stars that are spending most of their lifetimes far from the center of the galaxy and are just passing through? In the second installment of the COMB survey, where we did orbital analysis of our metal poor stars to be able to separate the stars into confined bulge stars and not confined stars, those halo interlopers, by looking at which stars have an apocenter less than 3.5 kiloparsecs. So what we see is if we looked at only the stars that have apocenters less than 3.5 kiloparsecs in the galactic center, we do see that the velocity dispersion is much lower than before when we have all the stars combined. And so it does actually match that boxy peanut bulge model with when we remove the halo interlopers. Interesting though, we do see in the confined bulge stars a signature of slower rotation than what's expected in the Milky Way based off of what we see for the metal-rich stars. So what we found out from this work is no, we don't find any evidence for a classical bulge component. We do have evidence for that boxy peanut bulge with an overlapping halo population that is causing that signature of a higher velocity dispersion in the metal poor stars. So next we'll go and look at the chemistry to dig deeper into some of these other possible origins. So one of the big signatures of a globular cluster star is this magnesium to aluminum anti-correlation. And this is specifically a signature of second generation globular cluster stars. And so you can see the majority of our bulge stars kind of fall along where the disk is, and the same situation we see in the halo. But then we do have these two stars up here, which are showing this high, very elevated aluminum values for their given magnesium abundance. And so that is an indication that they are second generation globular cluster stars. And one of these stars that marked with the X is actually a halo interloper, while this one is a confined bulge star, so it has an apocenter less than 3.5 kiloparsecs. Another key finding from our chemistry is that we find enhanced alpha elements in silicon and calcium for our most metal poor halo stars. And so what this indicates is that these stars were enriched by more massive stars than what we typically see in the halo, which is the green points here. And so that's consistent with our ideas of the first stars, since we think the first generation of stars would have had a top-heavy IMF. Next, we also look at kind of the more metal-rich ones, the really low alpha stars. We do see some stars that have much lower alpha abundances than the rest of the Milky Way, and that is a known signature of actually being part of an accreted system. But when we look and divide these stars up into the different dynamical populations we've defined, we find that those low alpha stars are primarily halo stars, so they could just be, from one of the many known accreted systems that we know of in the halo. So we don't really find any strong evidence for an accreted system among these confined bulge stars. And so to sum up what we found, it's possible we do find one confined bulge star that has a signature of a globular cluster, but it's much lower than some of the predictions and other measured rates for chemical signatures of globular cluster stars, specifically nitrogen-rich stars. So there's still some kind of work to be done to resolve this discrepancy and really characterize kind of what percentage of metal poor bulge stars are these dissipated globular cluster stars. We do not find any strong evidence for an accreted dwarf system among this confined metal poor bulge population, although there's maybe some for that halo interloping population. And then more work is also needed to figure out if there's any kind of unique systems or if they're already part of known systems. But last, we do find some chemical results that are consistent with what we expect for the first generation of stars. Specifically, we found those elevated alpha abundances that's consistent with that top-heavy IMF. So yeah, but always more work to be done to really study the origins of these stars and search for further chemical signatures of the first stars. And to really dive deeper into this, we would love to do a more detailed dynamical analysis of these stars. In order to perform a more detailed dynamical analysis, however, we require an accurate gravitational potential, which is currently under debate for the inner galaxy. There is a controversy currently over the length and pattern speed of the bar, which is essential to solve not only for intergalaxy dynamics, but the local velocity field is also greatly impacted. So here we're showing a figure that shows a comparison between the impacts of the two favored bar models on the local velocity field. So we have the short fast bar and the long slow bar, leading to very different structure in our local velocity field. And currently how we're trying to measure bar length, and historically how it's been done, is from red clump number densities. And so this is the number of red clump stars as a function of the K magnitude, which is a proxy for distance for red clump stars because they are standard candles. And so looking along different lines of sight, we can fit the number densities to bar models. And this is historically how it's been done. But my current work searches for another way to constrain the bar lengths and specifically to find a dynamical bar length by finding the last trapped bar orbit. But we also need to figure out, are we going to just retrieve a result completely impacted by the potential we assume, or is there actual information that we can learn from these orbits? So first, to answer this question, we look to n-body simulations. One of the models that we use here is shown in the middle panel, and we calculate the orbital fundamental frequencies for 10,000 random stars in this, and we can cleanly select bar supporting orbits in this area of this orbital frequency map. We can then take and you can see those points overlaid here on top of the bar. So it's a clean selection, even though we may miss some bar stars, but what we see is we can easily measure a bar length from the apocenter distribution by taking the 99th percentile. To compare, we also calculate the bar length from the number densities by calculating the Fourier decomposition of the distribution of stars and taking the m=2 component. And we can see that this results in a slightly longer bar length, which we've seen throughout our different bar models. But we can still move forward with our dynamically determined bar length, since that's what we'll just do an apples to apples comparison here. And so what we find is that basically what we do is we select 10,000 random stars from each of our models and calculate orbits for them in a ton of different potentials that have different bar lengths. And what we do is compare the bar lengths that we measure from the orbits compared to the potential bar lengths that we assume to calculate the orbits. And so we also know the bar lengths of the model from which we extracted the initial positions and velocities for the stars, which we show here as this black dash line. And we see that basically we only get a self-consistent bar length when the potential is consistent with the model stars. So we see basically that it crosses right at 0, right when we have when we're at that bar length that matches the model stars. And so that'll change depending on which model we've taken the stars from. And so that means basically that we can apply this to apogee data and find which potential leads to this self-consistent bar length, and that'll be the potential that is best describing the apogee and Gaia data. And so when we do that, what we find is a potential bar length of around 3.5 kiloparsecs. So what I'm showing here, these blue points is from one simulation, and we're taking different time steps from that as the bar evolves. And then the red points are from a completely separate simulation with totally different initial conditions, where we see it kind of follows the same trend. And so what we find is essentially a bar length of around 3.5 kiloparsecs. So in total, well, I'll just leave you with my summary here. I don't have time to go through it. But thank you so much for listening to my talk, and I look forward to interacting with all of you at the conference. Thank you.